Swayam Prabha. Digital India. Educated India.
So now let's try to reanalyze this circuit using the concept of the virtual short. Okay. So if there is 0 volt between these two nodes, what is the voltage at this node? What is the voltage at that node? So if there is a virtual short between the inputs of the op-amp, what is the voltage at this highlighted node? I will highlight it again, this node. So there is a question here, how is the gain infinite? Now that is the assumption we are using. Okay, we will design the op-amp to have a gain of infinity. Okay, now in reality, of course, you will never be able to reach infinite. You will reach a very large number. Okay, so you can think of this infinity as an approximation to a gain that is very large. Okay, is that fine? So what is the voltage here at the highlighted node in terms of the input voltage Vi? I think there is a problem here, but others are probably able to see the writings. There is, Anu, are you not able to see the writing? How about others? Anybody else has this problem of not being able to see the writing? No, I think maybe the problem is on your side. Perhaps you can quickly close the browser and reopen it. Perhaps it will be okay. So now hopefully the audio is also clear now. What I was asking was, what is the voltage at this node in terms of Vi? Okay. So if this is a virtual short, that is, these two have the same voltage, it means that clearly this node also has to have the voltage of Vi. Okay. So the voltage here equals Vi. Now, we also saw earlier that the current going here this way is 0. Okay. So clearly, if there is V naught here, the voltage at this point given by the voltage divider formula is V naught R1 by R1 plus R2. Okay. So what I have done is to determine the voltage of this through two different ways. One is by observing that this is a virtual short, it has to be equal to Vi, and another one is observing that the current here is 0. So if this point is V naught, this point has to be V naught times R1 by R1 plus R2. Okay. So clearly, whatever we derive for the same node from two different methods has to be equal to each other. So that means that V0 times R1 by R1 plus R2 equals Vi. Okay, or V0 equals Vi times R1 plus R2 by R1, or Vi times 1 plus R2 by R1. Okay, so I hope this part is clear. In this case, I did not assume that the op-amp was a voltage controlled voltage source with a gain of A0. I assume that the op-amp offers a virtual short between its inputs. Okay, so when it's a virtual short, we can immediately determine that the voltage here is Vi. It has to be equal to what you determine from the output, which is V0 times R1 by R1 plus R2. So by manipulating this, we see that the output is input times some gain, which is 1 plus R2 by R1. Okay, and that 1 plus R2 by R1 is exactly the gain we derived when A0 is very large. Okay, so when the op-amp is ideal, you can use the shortcut to analyze the circuit. Is this okay? Any questions? And op-amp is nothing but a voltage controlled voltage source with a very large gain. The whole point is you make the gain very large. It doesn't have to be very precise, but the gain value will not depend very much on gain. Okay, so for instance, you can make the gain let's say 10,000, but let's say for various reasons, usually when the temperature changes and so on, the gain will change. It could change all the way from 10,000 to 15,000 or 5,000, which is a very big change. Okay, but as long as A0 is very large, the gain will not change all that much. Okay, any questions? Okay, then let's move on with the lecture. So which part is not clearly understood? So which part would you like me to explain again? Okay, let's move on with the lecture. Now we can take another op-amp circuit. Let me do that. Okay. So let's see if it becomes clear after we do this circuit. Okay, so this is another circuit using op-amps, and now between these two nodes there is a virtual short. Okay, so that means that this point is at 0 volts, so this point is also at 0 volts. Okay. So remember, in case of an ideal op amp, there is a virtual short between these 2 points. Okay. But no current flows into the op amp. Okay. So in this case also, no current flows into the op amp. So now, because this is at 0 volts, what is the current through R1? Please try to answer this. What is the current through R1? So clearly, it is equal to Vi by R1. Okay. So we have Vi uh, across the resistor, and the current is Vi by R1. Now, I will not be able to take questions by audio. Any questions you have, please type it into the chat window. Okay. Now, this current, it can go either into the op amp or into R2. Now, we know that no current goes into the op amp. Okay, so it will go into R2. Now, what is the voltage drop across R2 in this polarity? So let me mark that here. What is that voltage across R2? Yeah, it is equal to V0, but in terms of Vi, what is the voltage? No, the voltage is not infinite. On the right side you have V0, on the left side we have 0 volts, so the voltage across it is definitely V0. But you also know the current that is flowing through it, so you can try and figure out the voltage across it. What is it? Yeah, that's correct. So clearly this current is flowing that way. So this current times R2 will be the voltage drop with the left side positive, but here I have defined it with the right side positive. So the voltage equals V0, which is minus R2 times Vi by R1, or V0 is minus R2 by R1 times Vi. Okay, so this is the gain. Okay, and because so this is another amplifier, that is a classic amplifier topology using op amps, and we analyzed it by assuming a virtual short between the inputs of the op amp. Okay. Any questions? Any questions about this circuit? So there is a question, is there any chance to change the gain of the op-amp by putting a resistor at the non-inverting terminal? Okay. Now we will see the condition under which the op-amp will behave like a virtual short, the op-amp inputs. And also, just to be precise, it's not the gain of the op-amp that is changing. Okay. The gain of the op-amp is A0, which is assumed to be tending to infinity. It is the gain of the circuit which is built using the op-amp. Okay. So the gain of the op-amp is A0 and that is fixed. There is another question, why feedback is used in op-amps. Now it is a particular type of feedback, that is negative feedback, that will create the virtual short. Now in this very basic course we will not go into depths of negative feedback. Okay, I'll just tell you that there has to be negative feedback and how to find it. Okay, how to find whether there is negative feedback or not. Now what I meant was the answer to earlier question. Now I will go through the conditions under which the op-amp input will behave like a virtual short. Okay. Now the resistor, it could be at the non-inverting terminal also, but we have to see. It depends on the topology. There are numerous topologies of op-amp circuits, and some of them have resistors only to the inverting terminal, some of them to both inverting and non-inverting terminals. Okay. And also, just to be precise, it's not the gain of the op-amp that is being changed. Okay, it's the gain of the overall circuit. The gain of the op-amp is A0 and it is fixed, and A0 tends to infinity in an ideal op-amp. So we have looked at two op-amp circuits. And in this circuit, V0 by Vi equals 1 plus R2 by R1, and we have this other circuit V0 by Vi equals minus R2 by R1. Now because the gain of the circuit on the left side is positive, it is known as a non-inverting amplifier. Okay, and because the gain of the circuit on the right side is negative, this is known as an inverting amplifier. Okay. So these are classic op-amp circuits, and by the way, these are true when the op-amp is ideal, which means A0 tends to infinity. If A0 is less than infinity, then A0 will appear in the gain expression for the gain, but as long as A0 is very large, the gain will be approximately equal to 1 plus R2 by R1. Similarly, the gain of the inverting amplifier will be minus R2 by R1. Okay. In fact, I encourage you to replace the op-amp by the control source in the inverting amplifier and calculate the gain. Okay. So you can take it up as an exercise. So if you replace this op amp with a voltage controlled voltage source, okay, because plus is on the bottom and minus is on the top, Vx, and this will be A naught times Vx with this polarity. Okay, so please analyze this circuit. It will be a general practice for circuit analysis, as well as then you take the limit of A naught tending to infinity, and you should get the same answer as what we got by assuming that the op amp input is a virtual short. Okay. Okay. Is this fine? Now, there is another question. What is the difference between neutral and grounding? Now, this is completely outside the scope of the basic electrical circuits. This has to do with safety and issues like that. The grounding is the ground wire is something that the ground wire in the household supply is a wire that is actually connected to the earth, so that, and the neutral is really what is connected to earth, and there should be a very small voltage difference between these two, so that you don't have electrical shocks when you accidentally touch electrical equipment and so on. But we can't deal with this here in detail, so you will have to go through other courses, mainly the ones that deal with power circuits, to understand this. But the concept is quite simple, and you can also probably refer to some standard textbooks to find out. Okay. Now I said that, so basically the rules for analyzing the ideal op amp circuits can be written down. First of all, what is an ideal op amp? This is an op amp. It's a voltage controlled voltage source with a gain A naught. Okay. And the current going into the op amp terminals is 0. Okay. And an ideal op amp means that the gain tends to infinity. Okay. So to analyze ideal op amp circuits, you can use the methods we used earlier, but you cannot write KCL at the op amp output. Okay, this is because you don't know how much current is going into the op amp. Instead, what you can do is to write the virtual short equation at the op amp input. Okay, so that is the two inputs of the op amp have 0 voltage between them. Okay. Now, I said that this virtual short condition is true only under certain conditions. So, virtual short condition, or rather, let me write it as Opamp inputs are virtually shorted under certain conditions, and that condition is only if the op-amp is in negative feedback. Okay, so this is a very important condition. You cannot assume that the op-amp inputs are virtually shorted in any circuit. Okay, in every circuit, the op-amp has to be in negative feedback in order for the op-amp inputs to be virtually shorted. Okay, I will tell you what this means. Okay, by taking the two examples. Let me take the non-inverting amplifier first. Okay, so let me take this circuit. Now what I will do is, I will null the input. Okay, that is, I'll set Vi equal to 0. So that means that I basically short circuit this to ground. Okay, then I will identify the input voltage Vx and the output voltage V0 of the op-amp. In this case, V0 is the output voltage of the circuit also. Okay, but as a procedure, you just identify Vx with the appropriate polarity, that is plus here and the minus there. Okay, let me call this V out. This is really the output of the op-amp. In this particular circuit, it is also the output of the circuit. Okay, you can have more than one op-amp in a circuit. Vx and V out of the op-amp. Okay, so then what you do is, you just remove the op-amp. Okay, let's say I remove this op-amp. And then you apply a test voltage to wherever the op-amp output was. Okay, this is V test. Okay, I just connected there. I remove the op-amp, and instead of the op-amp's output, wherever the output was, I connect a voltage source V test. Okay.